reiterate what we know. We've seen the design. You are given a description. Design a system that recognize a particular sequence. You are told that, so you have to come with the state table and then give somebody the circuit diagram. The steps still the same. You obtain the specifications, create the state diagram. That is where the brain is. Create a state table. Sometimes you don't really need, you can go straight to the state table, and then you determine the number of state variables or the number of flip-flops, then obtain the binary code, you perform state assignment, choose the flip-flops, derive the input and output equation, you draw the logic diagram. The first example was a sequence detector. You design a circuit that detects 3 or more consecutive ones. We said you have to understand how the connections are, input, output, and your clock. And then you have to understand whether you are designing a milli or a more machine. And then the most important thing is the state. Remember, a sequential circuit has got a combination circuit and the memory element. So what do you, the memory element keeps the memory of the machine. So what will you keep in memory? In this case, we said the number of ones that have arrived. If it is 0, the first one, second, third. Once you do that, then it becomes easy. We got our state diagram for milli and more. Then after that, just moving something here. After that, we got the state table from the state diagram. Go through those steps. We decided the number of flip-flops were 2. So we performed state assignment. We were calling it state 0. Now we have it as 0, 0. Then split the tables. And then we determined the flip-flop input equations from the excitation table. And then got the formula from that. Those are the flip-flop inputs. Then from that, we got the equation. Just go through all that. Then we got our equations. Then now this next step is just minimizing. Minimizing means you are getting a cheaper machine. You might end up using fewer gates. So, and then we had our circuit. That is our first example. Remember, we said that design is always the same. What we are going to do is just to deal with examples. We said implement the milli version of that. The second example is designing a sequence detector that detects 0, 1 with the JK flip-flop. Remember, the first one was a D. So we said the meaning of states. State 0 is 0 detected, state 1 is 1 detected. Then we got that diagram. Somebody should try and get a more diagram and tell me if you can get it. Then that is our state table. Then we do state assignment. We say S0 is 0, S1 is 1. Then we get that table. Then we look for the flip-flop input equations, JK, from this. We fill it, and then we get our equations, and then do the minimization. By the way, you can go straight to this kind of maps without that equation by just picking this one is for J, this one is for K, and that one is for Y. Then once you minimize, after minimizing, we got that circuit. Now, we need a parity check. Can you, on your own, now I'm giving you 3 minutes, you need a circuit whose input is asserted. The input goes to 1 when the parity is odd. That circuit is receiving bits serially on an input line. If it received odd parity bits, the output should be asserted. So that is what you need to do. Design a milli and more odd parity checker machine using a T flip-flop. Now, that is the question. Odd parity checker. Don't look anywhere. Can you decide what you will keep as the state? And then derive the milli and more state diagram. You can just do one. Once you've done that, I'm giving you 3 minutes, okay, to do that. Once you finish, just send me a chat. Okay, I need you to get the state diagram. That's the most important part. So can you do that? Okay, we will now continue. The time is up. So the first thing you need, okay, just do one, but let's continue. The first thing you need to do is, in this, what do you keep in memory? First of all, what is odd parity? It means the number of ones received are odd. Even parity, the number of ones received are even. So what do you keep in memory? You can't keep the number of ones. You can only keep whether they are even or odd, because from even you go to odd, from odd you go to even. So by so doing, the state, even state 0, odd state 1. So now you had that. Just observe it. You are in even. If a 0, you still remain even. If a 1 comes, they become odd. The output is a 1. If a 0 comes while you are here, you remain odd. The output is still a 1. If a 1 comes, they become even. Any problem there? Anybody with a problem? And then that is the more one. The output is a function of the current state. Look at where the output is. Even 0, odd, 1. You move. When you are even, 1 comes, you go that side. When you are odd, you go that side. So a more is lower. The output is associated with the state and appears after the state transition, while the milli is before. So that is the most important part. Then after that, okay, let's just do it. Can you determine from that? Pick one. Can you determine the state diagram? Call one S0, another one S1. Can you determine the state table from the state diagram? 2 minutes. I just want us to flow through. 2 minutes. When the first person to finish, just send me a message. Just write somewhere. We need to do it ourselves. We need the state table, present state, input, next state, output. Just okay. For those ones who have done, you should have something like that. Just observe there. That is your present state, input, next state, output. This side is milli, that side is more. Present state, input, next state, output. Remember more, the output is a function of the present state. So you can't have state 0 should have the same output. State 1 should have the same output. Self-correction. If you find a 0 and a 1 here, and you are the present state is state 0, for a more, you know you are going the wrong direction. Now, the next is assigning binary values to the state. So we say state 0 is 0, state 1 is 1, and then we draw the same table. We can't wait. So 0, 0, 1, 1, 0, 0, 1, 1. We get that. That is the encoded state table. We're just following the same steps. Now, the next one is we need to determine the flip-flops we are using.
Sorry, sir?
Yes?
Can I ask, is it possible that state 0, let's say it becomes 1 and state 1 becomes 0 if we assign it?
Yes, you should get the same thing.
Okay, thank you.
Yes, you should get the same thing in this effect. But 0, we look at it as reset. But in this one, it's the same thing. You will get the same final answer. Okay, so that is the excitation table. So now there you need the input, assuming you are using a D flip-flop. No, in this the question says we are using a T, the toggle flip-flop. So now you say if your present state is 0, your next state is 0, what should be T? You look at here, 0, 0, T should be 0 in memory. So you fill in that, you've got Y. Then you can fill in for what? For the more. In the exam, you'll only be asked to design one. If they don't tell you which particular one, you choose the one you want. If your present state for B is 0, the next state is 1, what is your T? It means it toggled, so T should be 1. You fill in that, and then we go, that is that, and then we go to the K maps. We normally don't plot the K map here. You've got AX, you've done that in your previous one. So this is what? TA. When A and X are 0, 0, when they are 0, 0, it is 0. When A is 0, X is 1, 0, 1, it is 1. Like that. That is how you plot that. And then minimize. You'll get TA is that, TB is that. And then after the equations, you get those are your two machines. Somebody can give you an input and the clock and might need you to tell him what the output is. So that is the machine that you are designing, the odd parity checker. We say the more is a bit slow, but it always has less components because the milli needs something connected to the output. So that is a design for the two. The steps are the same. That is why you need to do as many examples as you can. If you have a question, you stop me and ask. The next question, design a D flip-flop using a JK flip-flop. You are in the lab, you only have JK flip-flops and you want a D flip-flop. How do you realize it? You are in the lab, you only have this and you need a D flip-flop. How do you go about that? So the first thing is you need a D flip-flop. So you need a table with D, which is the input. You need a table with the present state, input D, and next state. That is what you need. Can you draw that table? You need a table with those. So draw that one. You want a D flip-flop. You know how it behaves. The question, that is what you want. So you've got A, input, the next state. Can you fill in that? Input will be 0, 1, 0, 1. A will be 0, 0, 1, 1. Then can you give me the next state? 2 minutes. Let's go for it. Just draw that. We are going through examples, but with examples, you must do them and ask questions. So 2 minutes, fill in that table. Okay, people are done. Remember, those people who are not following these things, you just need, it's very basic, but you have to attend class and participate. Okay, so where you want the functionalities of a D flip-flop. So you have 0, 1, 0, 1, all the 0, 0 of the present state. Remember, the next state of a D flip-flop is just what is at the input. So this and that will be the same. Now, those ones who did it, now you want to use a JK, understand design. You have JK to implement this functionality. This is basically what the state table gives you, how something functions. Now, you want to use a JK. So those ones who did it, can you have a J here and a K here? And I want you to do it. Add a J column and a K column and give me the values. You've got the excitation table here, the values of J and K for you to make a transition from 0 to 0 to remain in memory. What should JK be? You come here 0 to 0, J should be 0, X should be 0. Let's do it to completion. Continue. You will really enjoy when you do it by yourself. Somebody asked me a question that designing from a functional table. This is an example of defining from a functional table. Why did we not go to a state diagram? We can determine the operation, the function of a diff leaf from a table. It's easier to go straight to a table, but the process is still the same. So remember, we've not gone to a state diagram before a state table. We've just gone straight to a table because we know how the flip-flop, D flip-flop works. So it's not compulsory that you go to a state diagram. You can shoot straight to a table. All those are the same. They give you the functionality of something. So continue with J and K. So if you are in a lab and you don't have a D flip-flop and you have a JK flip-flop with some logic gates, you know what you should do. Okay, let's not waste time there. So that is what you have for J. That is what you have for K. Umeshan, you can use Boolean algebra instead of K maps. Just like you can use characteristic equations instead of what? In the other one, instead of a table, but most people prefer tables. That is why we don't go the Boolean algebra route. Is minimization. You can use any tool. Once you get the first equation of J, you can use any tool to minimize. So those ones who did that, that is what you have. You had a JK, all you need is a NOT gate to connect that and you get a D flip-flop. If you check carefully, that is why in master-slave flip-flops, the slave is always a D flip-flop because there is a NOT gate there. So you wanted a D flip-flop, you had a JK, you just need a NOT gate, then you've got your D flip-flop. The opposite, we are looking at flip-flop conversions. Can we deal with that? It's the same. Now, this time, we want a JK flip-flop from a D. We've got a D flip-flop. So what do? Let's just finish. Your inputs will be A, JK, next state. Where do you get this? From the behavior of a JK flip-flop. If it is 0, 0, it is in memory. 0, 1, it will be reset. 1, 0 set. 1, 1, it will toggle. 0, 0 in memory. And then you have a D. The D actually is just the same as the next state. From there, you get your K maps for just one input D, and then that is your circuit. Anybody with a question? We are looking at flip-flop conversion examples. Okay, next. Counter design. Design of counters. The design process is the same. You've designed counters in other ways, but now we are looking at a counter as a finite state machine, designing from first principles. So what do? Can somebody give me a state diagram for that, please? And you can use 0, 0, what as your states. What do you need to keep? A counter that counts from there to there, and repeats. Can you give me the state diagram? I just need a state diagram there. Quickly. Don't look at your notes. Let's just focus here and then you will cross-reference with your notes later. Can you quickly get a state diagram? Just draw it, and then once you finish, let me know so that we can move on. Online learning needs a lot of discipline. Nobody is watching you. You're probably in bed. You are even in the toilet, in the living room. So if you are not disciplined, it's going to be bad. And let me warn you guys from the head of department points of view. The pass rate in the previous semester was very high. Lecturers were setting list, define those kinds of questions, and they know that you can copy. and pass. The pass rates were extremely high. Listen to me. So now they are alarmed, they are aware. They've been told the kind of questions to set. Personally, in digital systems, you never got such questions. It was designed. My section, the pass rate was normal. So this semester is going to be, we have all learned, you have learned, the lecturers have also learned on the type of questions they should set. So you won't get the same things like what happened last semester. Pass rate was high, it was questioned. In the discipline, in electrical, there is only one course that had a low pass rate. The rest, they were very high. So the lecturers are going to tighten. Just know that. Because we are aware of your WhatsApp groups of answering questions. We are aware of helping each other. We are aware of you moving to each other's homes to do your exams. We are aware of that. It was a learning curve. So the setting will not be the same. To me, it doesn't matter. It will still be like last time. 3 questions, there will be 5 or 10 per section, random. You won't get the same questions. And the time is there to stop that. Okay? Mfundo? Okay, so those ones who did it, the state diagram is that. Anybody who has a problem, it's just a counter, counting from 0001, or you can, your arrows, most people prefer counting this side.
Prof, my question was concerning the test, Prof.
Yes.
I didn't do DS under lockdown, so I don't know how the answering system is. Do we write on paper and screenshot and send it to you? How do we answer the questions?
We mark all that. You can write on paper and screenshot, you can type in, you can have a PDF attachment, we mark all that.
Okay.
Yes.
Thank you.
Okay. Okay, so once you do that, there is no input. Remember, there is no output. It's not necessary that you must have an input or output. Don't force them. The excitation table is there. You've got the present state. They have already named them for you, next state, and you are using 3 flip-flops. So you should know where to get TA1, A2, A0. And then there is your K-maps. From that, you will minimize and get that. And then you get that count. You've designed it using other means, but here from first principles as a finite state machines. If you can put it in a diagram or a table, then you can design it. Okay, I need, just look at that. Most of you, not half of you, when you see a place with a long question, English and what, you just fail before you start. That's a very bad mentality. Can you get for me the state diagram of that question? 5 minutes. Whoever finishes, just send me a chat saying you finished. Yeah. The direction of the arrow does not matter. The arrow shows you are moving from point A to point B. So you can have A this side and B, and you go right, or you can have A this side and B this side, you go left. It's the same thing. The direction of the arrow, what matters is where are you coming from and where are you going, the transition. The physical direction of north and south doesn't matter. What matters is the beginning. What is at the beginning and what is at the end. If you flip the beginning and the end, still okay. Once I get over 10 people done, and then we move. You should get something like that. It's a counter, counts in one direction when the input is. Note that when you are doing that, you should tell me which one is your first bit and which one is your second bit. So check that. And then that is the table. Normally in an exam or test, we don't bring such long questions. That is just a counter with an enable. Any question here? Anybody with a question? So that is your present state, 0, 0. When the input is 0, 0, inputs are the enable and X. When they are 0, 0, you remain there. So you fill in that. And then you look for JA and KA, JB, KB from the excitation table. And then you go to those maps and then you will find that is your circuit. So I'm still insisting the most important thing is to get the state diagram or state table. After that, the procedure is the same. The next question is an arbitrary counter. Can you just check how that is designed? And I will take questions. I'm giving you about 2-3 minutes to look at it, and then I will take questions. Just see, check what is going on. I will take questions after 3 minutes. Okay, now let's go through it. This is a counter that counts 5, 7, 3, 2, 6, 5, 7, 3, 2, 6. Arbitrary sequence. With finite state machines, you don't need same number of steps and what you can design anything as long as you can quantify it into a state diagram. So that is our counter. We can binary code that with the binary value of 5, 7, 3, 2. Okay, so we've got our 0, 1, 2, 3, 4, 5, 6, 7, like that. It goes up to 7. 0 is not in our sequence, so the next state is don't care. Okay, but when you reach 2, 2 is our sequence. The next state is 6, so you go to 6 when you are in 2. When you are in 3 here, you go to 2. So you've got the current state, you've got the next state. These are don't cares. Then you can have your DA, DB, the flip-flop inputs. So DA, DB, DC is just the same as ABC. We know how a D flip-flop is. From this, you can now go to your K maps are drawn there, and then you can get your diagram. Same procedure. Now, there's one thing that I need to put forward. Remember here, 0, 0, 0 is not in our state, but it can happen. It can happen. So assuming your A, B, C is 0, 0, 0, what will be your next state? You have to work out from the connections. What will be at D? Remember, the next state will be what will be at D. So you have 0 there, 0 there, 0 there. Can you just reason and use what will be your next state? Sipo, you are saying 6. Luto, you are saying 110, which is what? 6. Any other answer? Okay, C's were the same. I'm still waiting for anybody. Okay, 110 or 6 Yashil is the same thing. Remember, in our design, okay, so all of you have said 6. Remember, in our design, what did we say? We said 0, 0, 0 is don't care. We used a don't care. So sometimes these out of sequence things, when they occur, you have to check and see what is going on. It must go. Okay, those ones who said 6, you are right. So now we are looking at what we decide. We said, assuming there is a 0, 0, 0, how will our system behave? 0, 0, 0 will go into 1, 1, 0, and then we go to a circle. Now, if you check, if you had a 0, 0, 1, it will still go to 1, 1, 0, and then it will never go back. If you have 1, 0, 0, the ones that are not in our sequence goes there and goes back. So there you have taken care of the anomalies. When you design such counters, you have to check those don't cares. if the don't cares don't go to the right sequence, for example, if that don't care comes here, and maybe this one doesn't go anywhere, you might be forced to put a value here. Are you getting that? There is nothing wrong to force this to be among your 5732 numbers. There is nothing wrong. If the don't care is misbehaving, you force it to that sequence. So those are the things that you need to take care of in designing arbitrary count. BCD counter design. We are looking, yes, a question there. The question is, how do we get 6? By looking at the connections. I will only do one, the rest you will do it. Let me move, I've got this bar here. It's making me not see properly. Let me just move it up. I'm gonna do one flip-flop, right? If this is 0, that is 0, that is 0. I'm looking at flip-flop A. What is D? D is connected to this, to B complement. This is A complement, B complement, C complement. You can see C is connected here, the complement is connected here, B complement, A complement. Those are the connections. So let's look at the DA here. DA comes from what? B complement, which is 1, and C complement, which is what? 1. 1 or 1 is 1. The next A will be what? 1. That is how they got 1 there. B is from C, which is 1, and the A complement, which is 0. 1 and 0 gives you that. The next step, you will find a 1 here for B. C only comes from A here. That is where it's connected, and that is 0. So it will be 0. The next, it will be 0. So that is where 110 was found. Are we okay there? Prenation, are you okay? Okay, that is how they found 110. You have to take care of those anomalies. So you have to check and say, assuming I had a 0, 0, 0, no, the next step will be a 110 and it will start functioning properly. So you have to check that. Now, the next is counter design. Need to move. Counter design. We are looking at counters. Any step. A BCD counter, 0, 1, 2, 3, 4, 5, 6, up to 9. You have your present state, next state counters normally don't have input, output. You have your flip-flops. In this case, they are 4. Basic design is just laborious. You can't get such a long thing in the exam. So those are your maps. Same procedure. Using the don't cares, you will end up with that. Your counter will look that. The procedure is the same. That is a BCD count. So, in summary, this is what I need to tell you, that the design follows the same procedures. The most important thing is to get something from once, from the description in English, the problem, understand it, and put it in the finite state machine language. How do you do that? Either a state diagram or a state table. And that is the most important step. Once you do that, the procedure is the same. So by now, you should be able, in summary, to do sequence detectors, flip-flop conversions, counters, and general finite state machines. In the assessment, what comes is the same thing. It's just that in the beginning, you have to reason out. I might not bring any of these things. You can even be given an encoder, a detector, decoder, all those. Just look at the question and reason out. Capture it into a model into a state diagram or state table. That is the most important part. Now, how do you acquire that skill? You acquire that skill by looking at as many examples as you can. You get experience. You will get something in the exam. If you've worked with it, you say, this one I've worked with it, and then things just go together nicely. So experience. Where are you going to get that experience? Looking for questions, deriving state diagrams. I've given you some questions in the tutorial. I've given you the scope of the first assessment, which is on third. The scope of the first, there will be 3 questions basically. The first question, the intro section. You will have 3 or 4 flip-flops that you need to derive the timing sequence. And in this case, because we are doing online, I will need your sequence maybe in 0s and 1s. The answer can be there, but getting it, you'll have to show someone how you did it. Okay. The second question is analysis of synchronous sequential circuits. The third question is what? Design. So you know the questions, but you don't know the circuit that will come, or the spec that will come for design, or the diagram, or the flip-flops that will come in the first question. Otherwise, you know the question. So just sit down and practice and prepare for the test. Next week, I've said you are going to take it and do a self-study on introduction to VHDL. And that is where the assignment comes in. Assignment is basically one of the assessments, will be based on that. Okay, so what are we saying? Next week, you will do self-study that will culminate into an assignment, which is one of the assessments. You've got 4 assessments. Assessment 1, which is test-like, is coming next week, Thursday. No, on third. Third is not next week. And then next week, you are going to do a self-study that will culminate into the second assessment, which is an assignment type to test whether you understand VHDL. And then you will be left with an assessment that covers the lab, where you will need to simulate things on the computer. And then the final assessment to wrap everything up. Okay, so that is what I had for today. I'm taking questions.